previous week, we looked at the vibrations of atoms in a crystal. So, what we considered was these atoms in one dimensional crystal and obtained the omega versus k for these systems, and then we related these to the planes of crystals vibrating in particular directions, and I gave you examples of these towards the end of those lectures. So, these are vibrating either like this or like this, transverse and longitudinal vibrations, and then we said that the quantum of these vibrations is known as phonons, and we gave the concept of phonons and then what energy phonons carry, and consider the crystal as a collection of phonons when these atoms are vibrating. We are going to take it a little further in this week's lecture and see what all happens when these phonons are excited and carry energy or the temperature of the crystal is raised. But before that, I need to also tell you about a different kind of phonon, and that is known as optical phonons or optical vibrations. I keep writing vibrations so that you realize that phonons are nothing but these quanta of these vibrations. So, just to recap what we had seen in the previous week's lectures was when I plotted omega k versus k, I got a curve which was like this all the way up to the Brillouin zone boundary, and the slope of these phonons at k equals 0 was related to velocity of sound. When we go further and consider more kinds of atoms in a lattice, then we will get some different kinds of vibrations in the crystal, and that is what we are going to discuss now. So, consider a crystal, again we will focus on one dimensions first. Consider a crystal with these crystal sites shown by crosses. And at each site there are two kinds of atoms attached to each site, let us say the blue one and the red one. The blue one and the red one, the blue one and the red one, and so on. So, let me just complete the picture. It is as if a molecule made up of two different atoms is sitting at each site. Now, example, this could be NaCl, NaCl or some other kind of atoms. So, this is like NaCl molecule sitting at each site shown by this cross. The distance between these sites is again A, so that the distance between the blue atoms is also A, and so is the distance between the red atoms. So, imagine this one dimensional crystal where these molecules are sitting here at each site, and now the vibration takes place. Again I am going to assume nearest neighbor interaction. That means the atoms from one site interact with atoms only to the next site, or the atoms nearest to them and nothing else. This itself brings out many features of the vibrations of this kind of system, as it did in the case of single kind of atom on a lattice. So, let us see now what happens in this case. So, I have these molecules sitting at these sites with different kind of atoms, which we can also call that now I have a basis at each site with two different kinds of atoms. I am just making 3 or 4 of them, because that is all I need to derive my equations etc. for the nearest neighbor. So, let me take this site to be Sth site, next one is S plus 1th site, and the previous one is S minus 1 site. And I am going to follow the notation or the book prescribed, that is notation same as given in Charles Kittle's book. So, one of these displacements I am going to call u. So, let us say at Sth site the blue one shifts by u s and the red one shifts by v s. So, that on the next site it will be v s plus 1 u s plus 1, and the previous site will be u s minus 1 and v s minus 1. Now, these v and u s and v s need not be of the same magnitude. Why? Because one atom could be heavier than the other, the heavier atom would move less, lighter atom would move more, and so on. So, these are two different kinds of atoms, two different kinds of motion, and now we write the equation of motion. Let us look at the blue atom, and for the blue atom the acceleration will be d2 u s by dt square, the force will be m, and this would be given by assuming the nearest neighbor interaction c, where c is the coefficient of the force or the spring constant, times the blue atom in the Sth site is interacting with the orange atom in its own site and one with the previous site. So, the force, and I will leave it for you to kind of work out, because we have been working this out for the one atom case, is going to be V s plus V s minus 1 minus 2 u s. Because if you look at the picture, I am going to make some wiggles. This atom at the Sth site is interacting with this atom and this atom, the previous atom. So, it is interacting with atom at the Sth site itself, but the other atom and the other atom in the previous site. Similarly, for the orange atom or the red atom, the acceleration is going to be d2 v s by dt square is equal to c. Now, this atom out here, the orange atom, I am showing it by an arrow, is interacting with the blue atom on the next site, and the same the blue atom on the Sth site. So, the force is going to be u s plus 1 plus u s minus 2 v s. These are the equations of motion. So, let us write them again. What I have done is I have taken this crystal with a basis at each point. So, blue atoms and the orange atoms, and at the Sth site the displacement is u s for the blue one and v s for the orange one, and then we have written the equations of motion is m d2 u s by dt square, is equal to C Vs plus Vs minus 1 minus 2 Us and m d2 Vs by dt square is equal to C Us plus 1 plus Us minus 2 Vs. Now, in writing these equations, you may have noticed so far I have made a mistake, and the mistake was that I have taken the masses of the atoms to be the same. They are actually different, that is why they are different kinds of atoms. So, I am going to put M1 and M2 here. So, these two atoms of different masses follow this equation, considering only nearest neighbor interaction, and now we again assume solutions like U s is equal to some amplitude u e raised to I k s a minus omega t, and V s is equal to some amplitude v e raised to I k s a minus omega t. This is a wave like solution that we considered for one atom basis, and substitute these in the equations. When we do that, I am going to get minus omega square m1 is equal to C V s is going to be v e raised to I k s a, e raised to minus I omega t is common and that gets cancelled from all the sides, plus v e raised to I k s minus 1 a minus 2 U s, which is going to be e raised to I k s a, and on the left hand side also I have a e raised to I k s a. So, this term is going to cancel from all sides, this s term will cancel, and you end up getting minus m1 omega square is equal to C v plus v e raised to minus k a minus 2, there should be a u. So, taking the equations to be m1 d2 u s over dt square is equal to C V s plus V s minus 1 minus 2 U s and m2 d2 V s over dt square is equal to C U s plus 1 plus U s minus 2 V s, and assuming the solution U s t to be of the form some u e raised to I k s a minus omega t, and V s to be of the same form, that is wave like form, v times e raised to I k s a minus omega t. When I substitute this in the equations, I get minus m1 omega square u is equal to C v plus v e raised to minus I k a minus 2 u, and for the orange one minus m2 omega square v is equal to C u e raised to I k a plus u minus 2 v. These are the two equations that I need to solve to get omega versus k graph. So, I am getting minus m1 omega square u is equal to C v plus v e raised to minus I k a minus 2 u, and minus m2 omega square v is equal to C u e raised to I k a plus u minus 2 v. I rearrange the terms, collect them all together, and I get these equations as 2 c minus m 1 omega square u minus c 1 plus e raised to minus I k a v is equal to 0, that is equation 1, and I get minus c 1 plus e raised to I k a u plus 2 c minus m 2 omega square v is equal to 0, which I can write in the matrix form as 2 c minus m 1 omega square minus c 1 plus e raised to minus I k a minus c 1 plus e raised to I k a and 2 c minus m 2 omega square times u v is equal to 0. And the solution I want is where u and v are non-vanishing. In such kind of cases, either the case is that u, v both are 0 and that is the solution, but we do not want that solution, because u and v we want to be non-vanishing, then only the wave is propagating. And to have that solution, I must have the determinant of the coefficient matrix to be equal to 0. And therefore, for the solution to exist, non-zero solution to exist, I should have 2 c minus m 1 omega square minus c 1 plus e raised to minus I k a minus c 1 plus e raised to I k a and 2 c minus m 2 omega square determinant must be 0 for the case when this wave exists, and that gives me 2 c minus m 1 omega square times 2 c minus m 2 omega square minus c square 1 plus 2 cosine of k a plus 1 is equal to 0, or omega raised to 4 m 1 m 2 minus 2 c m 1 plus m 2 omega square plus 4 c square minus 2 c square minus 2 c square cosine of k a is equal to 0. I collect the terms 4 c square and 2 c square here, and then write this equation as omega raised to 4 m 1 m 2 minus 2 c m 1 plus m 2 omega square plus 2 c square 1 minus cosine of k a is equal to 0. This is the equation to be solved to get omega versus k. So, this is a quadratic equation in omega square, and therefore, I can write the solution as omega square is equal to 2 c m 1 plus m 2 plus or minus square root of 4 c square m 1 plus m 2 whole square minus 8 m 1 m 2 c square 1 minus cosine of k a, this whole thing divided by 2 m 1 m 2, which can be simplified to c over mu plus or minus, I will take 4 c square out from there and you get 2 c. So, I can write this as c over mu again, and inside I get, I have taken out 4 c square m 1 plus m 2 square. So, I get 1 minus mu upon m, 1 minus cosine k a is 2 sine square k a, and there was a 2 left from when I took 4 out. So, times 2 sine square k a by 2 raised to 1/2, where let me write for completeness on the left hand side, mu is the reduced mass m 1 m 2 over m 1 plus m 2, and m is the total mass of the molecule. So, I get omega square is equal to c over mu plus or minus c over mu times 1 minus 4 mu over m sine square k a by 2 raised to 1/2. That is the solution for omega square as a function of k. Notice that it has two solutions. There is one omega 1 square, which is c over mu 1 plus 1 minus 4 mu over m sine square k a by 2 raised to 1/2, and omega 2 square, which is equal to c over mu 1 minus 4 mu over m sine square k a by 2 raised to 1/2. So, let me collect terms and write again omega 1 square is equal to c over mu 1 plus 1 minus 4 mu over m sine square k a by 2 raised to 1/2, and omega 2 square as c over mu 1 minus 4 mu over m sine square k a by 2 raised to 1/2. Understand that these two omegas which are there as a function of k. So, for each k I am getting 2 omegas. What do they mean and how do they look? So, let us to understand the behavior of omega k as a function of k, let me study them in the limit of k going to 0 or k a going to 0, that is very small near the center of the Brillouin zone. When I do that, for k a going to 0, I get sine square k a by 2 as k square a square by 4, and therefore, I can write omega 1 square as equal to c over mu 1 plus 1 minus mu over m k square a square raised to 1/2, which is equal to c over mu 1 plus, I can do the binomial expansion, 1 minus mu over 2 m k square a square, which is equal to 2 c over mu minus c over 2 m k square a square. So, near k equal to 0, omega 1 square is equal to 2 c over mu minus c over 2 m k square a square. How does it look? So, let us plot this. If I plot omega 1 k versus k, you will see that it has a value out here which is 2 c over mu, which I can also write that as 2 c 1 over m 1 plus 1 over m 2, and then it goes down. And then if you plot it fully, it comes down and comes to the Brillouin zone boundary minus pi by a and plus pi by a, like shown in the figure. You can also figure out what the value is near the Brillouin zone, because at Ka equals pi, I am going to have omega 1 square is equal to c over mu 1 plus 1 minus 4 mu over m raised to 1/2. So, this is going to be slightly less than 2 c over mu. So, it goes down. So, this is how this omega 1 square looks like. So, I have this mode which is has frequency omega not equal to 0 at k equal to 0, and then it is almost flat. This is known as optical phonon, for reasons will I explain a bit later. Let us look at omega 2 now. When I look at omega 2 square is equal to c over mu 1 minus 4 mu over m sine square K A by 2 raised to 1/2, and this for K A going to 0 goes to c over mu 1 minus 1 plus mu over 2 m k square a square. So, this is equal to c over 2 m k square a square. This is exactly like what we had earlier in the acoustic mode that we studied last week for a single atom system. So, this is the acoustic mode, and in this case omega k versus k goes exactly like a single atom mode. So, this is known as the acoustic mode. So, in general, when I have these two atoms per lattice site, let me make them completely. They have these two frequencies, and let me plot the frequencies versus k within the Brillouin zone. Because that is the only k that matters, and we have really understood it last week. One mode is like this, almost flat omega k versus k, and one is like this. This is known as the acoustic mode, and the upper one as the optical mode. At k equals 0, the values for the omega for optical mode is 2 c over mu, and this is 0. So, you see that when I look at 2 c over mu, which is 2 c 1 over m 1 plus 1 over m 2, it is a vibration as if the atoms are vibrating within themselves, right. It is as if it is a vibration of this atom with itself, right. That is why the reduced mass is coming, and c is the strength of this interaction between the atoms, whereas the acoustic mode is carries c over m, and then it is as if this whole molecule is acting like one system, and they are connected with this c interaction strength, and this whole molecule is vibrating like a single unit. So, optical mode is where the constituents of the bases vibrate against each other mainly, and in acoustic mode is where this whole thing vibrates as a unit. Now, you may ask why I am calling this an optical mode. Recall from the previous week that if I want to excite these modes using some external excitation, and last week we studied how neutrons are used or other particles or interactions are used. When we considered light, we found that lambda for light is almost of the order of 5000 angstrom, and k light is 2 pi over 5000, which is much less than k phonon, which is more like 2 pi over 1 angstrom. So, it is almost 0. So, light does not really transfer any momentum to the phonons. For the acoustic mode, if it does not transfer any momentum, it will hardly transfer any energy also, because for acoustic mode as k goes to 0, there is no energy absorbed. On the other hand, for k equals 0, the optical mode does have an omega which is non-zero, and therefore, it can absorb energy. So, these can be excited using light, and that is why these are called optical modes. Now, in the next lecture, we will study how these modes then can be counted and how the energy stored by them at temperature T then gives you the specific heat and other properties of solids.